Today we're going to be talking about limits at infinity. Whereas before we were finding the limit of f of x as x approached a very specific number a, and we either got a limit, an actual number, or infinity plus or minus infinity, or maybe it didn't exist. So here, for example, remember we found the limit as x got closer and closer to a from the left and from the right. This reached a certain output value of L. Or it could shoot all the way down to negative infinity. It could give me an output value of negative infinity, which of course, infinity being an idea, does not exist. Now take a look at the difference of what we're going to be learning today. We are now looking for the limit of f of x as we push x out to positive infinity, plus or minus infinity actually. Now that means we will have some sort of x value, and we are looking to see if this output value, right, if we increased x, push this all the way out to the right, up to positive infinity, will this output x reach a maximum value, or will it continually increase? In this case, maybe really slowly, but it will continually increase forever. Okay, so if it actually does reach a maximum, we consider the limit there to be a limit. If it does not, then of course the limit does not exist. It could be plus or minus infinity as well. So now let's take a look at some examples then. So in this example, we have the function x squared minus 1 all over x squared plus 1. The graph looks something like this. Now what I've done here is I've made an x that's movable. Right, so I can make x very small. I can make x equal to 1, which if you take a look at the output should reach, yep, 0. Because if I plug in 1 here, if you calculate it, my output is 0. Or I can increase it and push it out. And notice how the output, 0.56 here, this output, 0.56 somewhere around here, will also increase as I move this point. Now, as I push x out, all the way out to positive infinity is what we're going for. Notice how the output here is also changing. It is increasing, but will it reach an actual limit? I'm going to zoom out a little bit here and take a look. 0.97, 0.99. Will it reach 1? It looks like it does reach 1. I'm going to zoom out some more. 1, it looks like, I mean, graphically speaking, it definitely looks like the limit as x approaches infinity is 1. And we will be learning how to prove that in just a little while. Let's look at a second example that we actually do know the limit for. This one right here. F of x is equal to the arctangent of x. Now in this case, if you remember what the arctangent was, it's basically one of the curves of the tangent graph inverted, right? Inversed, if that's a word, where we switch the x and the y's, the input and the outputs. So here at this point, if you remember, when we increase this, it definitely does reach a maximum output. It will never go beyond a certain number. It will get infinitely closer to a certain number without ever reaching it, and that value was pi over 2. So remember, pi is 3.14 divided by 2 is approximately 1.53. Now that is how we define our horizontal asymptotes. Our horizontal asymptote is defined as the line y equals to a certain value. So again, it's some sort of a horizontal line. So y equals L is the horizontal asymptote of the function f of x if the limit of f of x as x approaches positive or negative infinity is equal to a certain constant. So if it doesn't shoot up forever and ever to positive infinity or shoot down to negative infinity, you have what we call a horizontal asymptote. So now let's look at one more example. Our function 1 over x. Now this will become a very famous one that we use very often because this function right here, I'm going to move it over here, as x approaches positive infinity, if you remember, I'm going to zoom out quite a bit. We'll get closer and closer, if you remember, as the denominator gets infinitely big, the output will get smaller and smaller, closer and closer to 0 without it ever reaching 0. Same thing for the negative side. If I plug in negative values, where the absolute value gets bigger and bigger and bigger and bigger, this output, as this denominator gets, or the absolute value gets bigger, this output will get closer and closer to 0. Right? So this will now become a theorem that we use quite often, is the fact that the limit as x approaches plus or minus infinity of the function 1 over x is equal to 0. So now this is what I'm going to use in order to prove this limit right here, to see if a rational function, this one right here, 3x squared minus x minus 2 all over 5x squared minus 6x plus 1, does this have a horizontal asymptote or not? And we are going to prove it by using this theorem that we just learned. Now please take a note that this is the difference. We have been working with rational functions as finding the limit as x approached a certain number. Remember, what we wanted to do when we had a number was to try to plug it in. And if you plug in 1 here, you get 5 minus 6 plus 1. So we do have a domain issue. So we factored it magically. And when we factor the top to equal this and this, we can cancel. And the limits are now the same. So all I have to do now is plug in that 1. I get 3 plus 2. I get 5 on top. And then 5 minus 1, I get 4 on bottom. So again, that's if we're looking for the limit as x approaches 1 for a rational function. In this case, so this is our review. In this case, we're now looking for a limit as x approaches infinity. So these two functions are pretty comparable. It's an x squared function. The 2 is the highest degree. 2 is the highest degree on the bottom. Does this reach a maximum output, a limit, to have a horizontal asymptote, or will it increase incrementally, very, very, very slowly? We're going to use this fact right here. Now I want to change each of these terms to be 1 over an x value. So the way I'm going to do that is I'm going to multiply top and bottom by 1 over x to the second power, because that is the highest degree that I have here. And on the bottom as well, this is the highest degree, 1 over x squared. When I distribute that, I get 3 minus 1 over x, because these x squares canceled, and then the top one cancels, there was 1 left on the bottom, minus 2 over x squared, all over 5 minus 6 over x plus 1 over x squared. Now if I do this, take a look at what happens. This will now reach 0. This term will now reach 0, so will this one and this one. So the limit will equal to 3/5. Now what does that mean? That means as x gets bigger and bigger and bigger, there will be a maximum output that it will try to reach with infinitely. It will reach this term as x approaches infinity. So there is a horizontal asymptote at y equals 3/5. So let's try this next example. We are looking for the horizontal and vertical asymptotes of f of x. Horizontal asymptotes will be defined by the limit as x approaches positive infinity of the square root of 2x squared plus 1 over 3x minus 5. We will also need to find the limit of square root of 2x squared plus 1 over 3x minus 5 as x approaches negative infinity. The vertical asymptotes will be found where the limit as x approaches a certain number a of this function. Now if you take a look, there's only one possible vertical asymptote, and that is when the denominator is equal to 0. because I can plug in any number into this x and it won't give me any issues. So when 3x minus 5 is equal to 0 is the possible a that we want to choose. So at around 5/3, at exactly 5/3, right? So the horizontal asymptote here. Now we want to get each of these terms to look like 1 over x. In this case, it looks like, I'm going to erase this one for now. We'll do it again later. In this case right here, it does look like I have the square root of this entire term, 2x squared plus 1. I can't just divide both sides by an x. What is the highest degree here? The highest degree happens to be 1. Because in this case, it's not a 2, it's not x squared, because we are going to eventually square root that. So the highest degree is 1. So what I'm going to do is multiply top and bottom by 1 over x. Now on the bottom, that's easy to distribute in. On the bottom, I get 3, the 2x's cancel, minus 5 over x. But how do I distribute this x into this square root? Well, I can't, because this is on top of the square, not in this form at least, because this is inside a square root and this one is not. But I can change this to look like the square root of a square. Is that not the same thing as just x? It is. But now we've put both of these under the square root, and now I can distribute in. So I get the square root of, I'm going to do 2x squared divided by x squared, 2, plus the 1 divided by x squared. Right? So now if you take a look, it looks like this term right here will reach 0. So I get the square root of 2 on top, and this term will reach 0, giving me 3 on bottom. Now I do have to check, so there is a horizontal asymptote at y equals square root of 2 over 3. Right? We do still have to check the limit as x approaches negative infinity though, because it does look like the negative values do make a difference. Now if you notice, if I plug in negative values here to get bigger and bigger and bigger, it's always going to come out positive. This is the only number that will change. So if we go through the same process all over again, we're going to get the exact same thing except for the fact that this denominator will always be negative while the numerator stays positive. So there is a second horizontal asymptote at negative square root of 2 over 3. Now in this case, we are going to take a look at the graph. There's nothing that looks like that we can simplify in this case. So we're going to take a look at the graph here, which if I can pick up, looks like this. So here, at positive square root of 2 over 3, we have a horizontal asymptote. Here at negative square root of 2 over 3, we have an asymptote. And then we have a vertical one here at 5/3. If you notice, in this particular graph, it looks like our graph does cross our horizontal asymptote. But with this definition, with our calculus definition of horizontal asymptotes now, we learn that it doesn't really matter what happens at these small values. Horizontal asymptotes are defined only when x values are really, really, really big, particularly at infinity. So in this case right here, this does not mean, this is not breaking any laws here. It's at when x goes to negative infinity where it reaches that horizontal asymptote. Now real quickly, here are some 4 more examples. The limit as x approaches negative infinity of e to the x gets closer and closer to 0, because negative exponent will flip this into 1 over e to the x. And then limit as x approaches infinity of log of x actually looks like it reaches an asymptote, but it does not. It forever increases, albeit very, very, very slowly. The limit of sine of x as x approaches infinity, it maxes out at 1, so that it does not positive or negative infinity, it just does not exist. And then here, the limit as x approaches negative infinity of x cubed is negative infinity.